Hello everyone. Today we are going to look at the second part of section 6.1, which is projectile motion with angles. Our learning targets today are to be able to describe the horizontal and vertical motion of a projectile launched at an angle, and to be able to use our equations to analyze the motion of projectiles launched at an angle. So we're going to start by looking at how these are different from the horizontal projectiles that we have been looking at. So your picture here on the left is a horizontal projectile. Remember that this one gets launched in a straight horizontal line, and then gravity grabs it and starts to pull it down. And so it moves in this kind of an arcing fashion here as gravity pulls it down, and it's still moving forward. On the right, here's our projectile that comes up at an angle. So when this person lets go of this projectile, see how it's not coming straight out of their hand. And in this projectile, we're going to go up, right? And it's going to slow down till when you get to the top. And then as it comes back down toward the ground, it's going to speed up again. We talked about this way back in like October when we first got introduced to the idea of objects in free fall. So what I'd like you to do is take a moment and stop the recording and think about how these things are similar and how they are different. So stop the recording, write down a couple of thoughts, and turn it back on when you're ready. Okay, I hope you really did that. The couple of things that I really want you to recognize are that these things are similar. They still have independent vertical and horizontal motion, right? So this is tricky. It's always tricky. But as the things are going up and down, they're also going forward. Okay, and it's just one of those things. And then if you look at the trajectory of it, right, the trajectory is the path of the projectile. The trajectory is an arc. And that's because the object is not only moving forward, it's also moving up or up and down. Okay? How are these things different from each other? Well, pretty obviously, the one that has an angle goes up first. I should put the angle in there, shouldn't I? So the angled projectile goes up, then down. And here's the one that's going to be the biggest difference for us. Up until now, our initial vertical velocity has always been 0, but in a projectile with an angle, our initial vertical velocity is not 0, right? There's going to be a value. And this is where our vector skills are going to come in handy again, because that's how we're going to find the value of that initial vertical velocity. Okay, so let's kind of summarize a little bit. If we look at our chart here, does our angled projectile have velocity? Yes. So it has a Vx, and just like in a horizontal projectile, our Vx is constant. Does our object have vertical velocity? Yes, it does. We are going to have a VIY, that's a number with value. Should have made my boxes bigger, huh? And in this case, our VYF, our final vertical velocity, is going to be 0. And the reason that it's 0, I'm going to scroll back up to this picture again. We've talked about this before. Remember what has to happen as our projectile goes up. When it gets to the very top here, we have to have a value of 0 meters per second, because our thing has to change direction, right? And if it didn't come to 0, then it would just keep on going up. So up here at the top, this is where our VYF is 0. Okay, back down to our chart. Horizontal, do I have acceleration in the horizontal direction? I do not. So our acceleration in the horizontal direction is 0, right? There's no horizontal forces, there's no horizontal acceleration. How about in the vertical direction? Do I have acceleration? Absolutely. In our vertical direction, we know acceleration is going to be due to gravity, and so that value is still going to be 9.8 meters per second squared. Does our angled projectile have a range? You bet it does. Remember that dx is the horizontal distance and range. Okay, so that the dx is going to be where it lands. Do we have a vertical range? We don't. That's why there's x's there. Do we have a horizontal height? We don't. Do we have a vertical height? Absolutely. So our vertical height here is still going to be h, or remember we could also call it dy, right? Same thing. And our horizontal our vertical height, our vertical distance is going to be in the middle of the trajectory. Because this time our projectile goes up first, right? Gets to a maximum height and then starts to fall. Okay, how about time? Does our horizontal motion have time? Absolutely. Does our vertical motion have time? Absolutely. So the time is the same for both horizontal and vertical motion. All right? So what's our big idea here? Our big idea is that angled projectiles have initial horizontal velocity and initial vertical velocity, but they are still independent of each other. Okay, and one more time, we are going to highlight that word independent. When you define projectile on a test, you are going to need to remember that the vertical and horizontal motion are independent of each other. All right. So let's go ahead and do ourselves a practice problem here so that we can get used to how this is going to look. We'll take a minute and we'll put our formulas in here again. I know I make you write these all the time. The more often you write them, the better you're going to remember them. So here we go one more time. Horizontal formula, dx equals vx times t. Remember that dx is the range, vx is the horizontal velocity. Vertical formulas, h equals 1/2 gt squared. H is the same thing as the vertical distance, and we often use this formula to find time. Formula 3, VFY equals VIY plus A times T. Remember that's the final vertical velocity is equal to the initial vertical velocity times acceleration, plus acceleration times time. And acceleration, remember, is going to be 9.8 meters per second squared because we're on the Earth. And last but not least, VFY squared equals VIY squared plus 2AH. So again, final and initial vertical velocity. Acceleration is still due to gravity, and h is the height of our object. So in a twist, we are actually going to use this one today to find height, because we're going to know both velocities, but we're not going to know a time, and we're going to try and find height. So just FYI, coming up, we're going to use this to find height. Okay, let's take a look at our problem here. So this is a really complicated drawing, but I'm going to draw your attention to a couple of things. This, they say VO, you say that V naught, actually. This is our initial velocity. Notice I didn't say vertical or horizontal, it's just initial velocity. And then here is our angle down here, okay, the angle that this object was launched at. In the very center, we have our maximum height. Along the horizontal down here, we have our range. And although it's not written on here, we know that our acceleration is going to be due to gravity. And on the way up, it's going to slow down. So as my projectile moves up, the velocity is going to get smaller. The velocity up here at the top is going to be 0. And then as it falls, the velocity is going to get faster again. Okay, so got that all in your mind? Let's jump right in. Okay. Okay, so given a launcher with an initial velocity of 12 meters per second, so that's important, at an angle of 25 degrees, that's important, we want to calculate the time, we want to calculate the maximum height, and we want to calculate the range. So that's a lot of things. And we're going to take it one step at a time, as you can see down here. So step 1 says, label the diagram with the initial velocity and the angle of the launch. So here's our diagram. This black arrow, that's our initial velocity. So we're going to say v equals 12 meters per second. And down here is our angle, and we're going to say that our angle is equal to, sorry, what did I say? Oh yeah, 25 degrees. All right, if you don't already have your calculator out, go ahead and pause this video, grab your calculator, make sure you hit that mode button. You should be in degree mode, not radians, degrees. All right, and then pick it back up when you have your calculator and you're set to go. So we're going to start by finding the horizontal velocity and the vertical velocity of our object, and we're going to use our vector skills to do that. So if we want to find something in the x direction, we know that Vx is going to be equal to the initial velocity times the cosine of our angle. When we did this before, we called everything r, but now we know it's a velocity, and so we're going to call it v. So we're going to say Vx is equal to 12, because that was the initial velocity, times the cosine of 25 degrees. Stop and think about where those numbers came from. All right, you're going to plug that in your calculator. If your calculator is set correctly, you are going to get 10.8, and we're going to round that to 11 meters per second. So what did we just find? Let's go back up to our diagram. And this red arrow right here, this is my Vx. So Vx is equal to 11 meters per second. Remember that Vx is constant, and so on the whole horizontal path here, the Vx is not going to change. Okay, so there we go. That's part of it. We also have to find our initial Vy. Remember, this is not 0 anymore, right? Because it got launched, and so it's headed up. So just like we found Vx using our vector skills, we're going to find Vy the same way. So we're going to have Viy, initial vertical velocity, is equal to v times the sine of my angle. So I've got Viy equals 12 times the sine of 25. Stop and think. Do you know where all those numbers came from? All right, you're going to put that in your calculator. We're going to have Viy equals 5.07, and we're going to call that 5.1 meters per second. All right, if I go back to my drawing, that's the blue arrow right here. So this blue arrow right here, that's my Viy, and we know that that's 5.1 meters per second. Now we also know that our Viy is going to change, right? As it goes up, just like this, it's going to get slower and slower and slower and slower, right? Because gravity's pulling on it. And so up here at the top, I have my Vyf, and that's going to be 0 meters per second. Then it's going to start speeding back up again on the way down, and by the time I get down here, we're back to our Vy being 5.1 meters per second. But the part that we care about is this first half. So we really aren't going to do anything with the second half of this. We really are just going to focus on the first half, all right, of our picture here. So now we have our initial vertical and horizontal velocities. We can find the height. Remember I told you we were going to do this a little bit differently. So we're going to use our height formula, not our regular height formula, our other height formula, because right now we don't know the time, so we can't find the height. So we're going to use VFY squared equals VIY squared plus 2AH. We know that VFY is 0 squared. We know VIY is 5.1 squared because we just found that out. 2A is 9.8. Sorry, 9.8. And H is what we're trying to find. Now stop for a second and think about this. Okay, this is also going to go way back to like October. If you have an object that's slowing down, it needs to have negative acceleration, right? Because it's slowing down. So when we put 9.8 into this formula, we're going to call it negative 9.8 because we know our object is slowing down. So now I'm just going to do some algebra here. 0 squared is 0. 5.1 squared is 26. 2 times negative 9.8 is negative 19.6. And there's my H. I'm going to subtract 26 from both sides. I'm going to get negative 26 equals negative 19.6 H. Divide both sides by negative 19.6. Oop, ran out of room. Okay, and I'm going to end up with H equals 1.3 meters. I did that really fast. If you want to pause and go back and make sure you can do that on your calculator, that's a really great idea. Okay, so now what did we know? Now we know that this distance right here, our maximum height, is 1.3 meters. H equals 1.3 meters. That's as high as it's going to go. Okay. All right, step 4. This is a lot of work, isn't it? Step 4, now we need to calculate the time. Now notice there are 2 time things here. I have time to reach the maximum height, and I have total time in the air. Those are 2 different things, okay? We'll talk about why that is in just a minute. So let's find the time. Now I know the height, so I can go ahead, and we're used to doing this now. So I'm going to plug in my 1.3. I have 1/2 times 9.8. It can go back to being positive now because we're not slowing down or anything. And t squared. So I'm going to have 1.3 equals 4.9 t squared. Where'd the 4.9 come from? Good. Okay, we're going to divide everything by 4.9. That cancels out. I'm going to end up with 0.265 equals t squared. I have to take the square root of that, and I'm going to end up with t equals 0.515 seconds. Okay, so if we go up on our drawing now, what happens in those 5.1 seconds? In those 5.1 seconds, my object goes from way down here at the beginning up here to the top. And that takes 5.1 seconds to go all the way up. Okay? Now I need to know the total time it's in the air. So if it takes 5.1 seconds to go up, how long does it take to come down? Absolutely. If it takes 5.1 seconds to go up, it takes 5.1 seconds to come down. So the time over here is also, I'm sorry, not 5.1. Boy, did I mess that up. 0.515. Woo, that would be a biggie, wouldn't it? Okay, hang on. All right, so this should be 0.51 seconds. And this should also be 0.51 seconds. Wow. Boy, oh boy, oh boy. So sorry. All right, so my total time in the air is 0.51 seconds to the top and 0.51 seconds back to the bottom. So we're going to say our total time is 0.51 times 2, which gives me 1.02 seconds. That's my total time in the air, from the time it takes off to the time it lands. All right. Now the last thing we want to do is find the range. How far is this thing going to go? And so remember, range is the same as dx, so I have dx equals vx times t. Dx equals, well, let's see, we figured out Vx way back here at the beginning, so Vx was 11, right there, Vx equals 11. So my Vx is going to be 11. And then I need to decide, do I want to use the half time, this one, or do I want to use the whole time? What do you think? Yeah, good for you. We want to use the whole time, right? Because we want to know how far it's going to go. So we're going to use the whole time. So we're going to say 11 times 1.02. And we're going to get dx equals 11.2 meters. Okay, and if I go up here to my drawing, a lot of colors today. Here is my range, right? My horizontal distance. And I just calculated that that is going to be 11.2 meters. Okay. All right, so I did that really fast, but the beauty of recorded notes is that you can go back and listen again if you need to. Down here it says your turn, and there's a problem for you to do as well. So let's take a look at what I'm going to ask you to do here. I'm telling you it's 65 degrees and 7.5 meters per second. So that's just the same information you had in the example problem. I want you to label the drawing. I want you to calculate the predicted landing spot. So that's the range, and I want you to use the same steps as we did up above. So I wrote them out for you down here. You're going to do step 1, and then step 2, and then step 3, and then step 4. And you're going to do it exactly the way that we did it in the example problem. When you get done, I want you to check your answers, okay? The sub has the answer key, so go see if you did it right, okay? If you are confused or stuck, we will look at this again the next time I see you. But like I said, the beauty of recorded notes is you can go back and listen to them again. So if you're stuck, try it again. Thanks so much. I'll see you guys later.